Welcome everybody to your free GMAT prep hour. It is October 24th, 2021. We are a week away from Halloween. I hope everyone is gearing up with their costumes, ready for trick-or-treating, all that jazz. Should be a more fun Halloween than last year. So hopefully y'all are ready to get out there and get back to that tradition. My name is Reed. I will be your guide through the wonderful world of the GMAT today. As usual, I'm going to plug the other free resources that are available to you if you're looking for free resources. You can try the first class of any of our classes for free. That is 1/9, over 10% of an entire GMAT course that you don't have to pay a dime for. You show up. We talk about some major stuff in class 1. We talk about how the test works and how to study for it. We talk about data sufficiency, give a solid overview of that and some of the major strategies you need for data sufficiency. And we talk about sentence correction and some of the major strategies you need for sentence correction. Okay. And again, you don't have to pay a dime. Go sign up for a course, show up. There's no reason not to. Free 10% of a GMAT course. If you like it, great, sign up for it. But honestly, it's useful advice for anyone studying for the test. You can do a similar thing for our Interact course. That's our self-paced video study program. It's a nifty little program that adapts to you as you go through. So if you get a question right, the program will say, great, you got this right. Would you like a harder question? And you can go to a harder question. Or if you miss it, it says, okay, you missed this question. Let's dive a little deeper and maybe, dig into the foundations, do an easier question, and then come back and make sure everything's built up. So it's a really nifty way to do a video course. Also, in the last 6 months or so, I am proud to announce that our Foundations of GMAT Math course is now totally and entirely free. We do 1 or 2 a month. It's a 7-hour course, either all in one day, or sometimes we break it up over 2 days. Really, really wonderful course. I honestly think that anybody would get something out of that. I got something out of it after having taken the GMAT and taught at the company for a few years before I first sat down for that course. It's just a very interesting course. We talk about the core foundations of math in a very GMAT way. Talk about some ways to handle arithmetic since you're not allowed a calculator in the quant section. We dig into the rules of divisibility. We talk about percents at like a really foundational level, give some nifty tricks for how to think about those problems. So it's just a really good course for people who need to dust off their foundations of math and people who are pretty into this. Just if you want to think about math in a more GMAT way, in a way that is frankly the way I wish I had often been taught math in arithmetic and whatnot. So take a look at that Foundations of GMAT Math course. Again, totally free. If you can't make one of the workshops, you can get all of the resources, a video recording of a workshop and our course syllabus and the worksheets we give totally free as well. So free resources out there for everybody. Take advantage of that. So today we are going to dive into a lesson. I'm not going to say what it is quite yet. I'm going to pull up a few questions. Before I do that, just a quick overview of what data sufficiency is. Some of you probably studied before, so you know what it is, but for those of you that have not, data sufficiency is a very GMAT specific question type, kind of unusual. What you're going to do, what you're going to see is you're going to be asked a question up top, and then you're going to have two statements about the situation. Okay. And the goal is not really to answer the question that is asked. The goal is to determine what combination of information in the two statements would be sufficient to answer the question that is asked. Okay. And the answer choices are always in this order and always with this language. We have a nifty little mnemonic to help people remember those answer choices: 12, 10, 1, 2, TEN. That's how I remember the order of the answer choices: 1 alone, 2 alone, together there's enough, either alone there's enough, or there's just not enough overall. I cannot answer this question. Okay, so I'm going to pull up a few questions here in a moment, and you're going to find some of them are data sufficiency. I'm going to keep a little box with these answer choices here in the corner to remind you what they are. As you study, eventually you'll probably just have them memorized. But for now, if this is day 1, I just want you to know what's going on there. Okay, and I know that's very fast, so if you're still a little lost, that's fine. What I'm about to do is I'm about to pull up a page that has 7 questions on it that all deal with today's topic. And if I gave you full GMAT pace for those questions, you would have 14 minutes. It's a free GMAT prep hour, and that's a lot of time. So what I'm going to do actually is I'm going to give you 8 minutes, which is still a lot of time. So this will probably go a little bit long for those of you here today. If you have to leave, of course, feel free. But I'm going to give you 8 minutes to pick and choose strategically which of these questions you want to spend time on, with the goal being to get as many right as possible. I think this is a good drill to do from time to time to facilitate or to practice the decision-making aspect of this test. This test demands that you decide where to invest time. It's not so much a game about getting every question right. In fact, you really shouldn't expect that. Even people who get great scores miss a handful of questions. I have missed 11 questions on a practice test and gotten a 50 in the quant. That's the second highest score possible. 11 out of 31 is more than a third of the questions. Okay, so you can miss a boatload of questions and still get a really great score, but you have to invest where you put your time wisely. You know, you have to do questions that you think you have a good chance of getting, and those questions that are a little bit gnarlier, you might just let them go. You might just say, I don't know how to do this today. I'm going to skip it and move on. That's totally fine. That's always going to happen. So this drill is partially to facilitate that. It's also just for the sake of time. For those of you that are watching the YouTube video, I recommend you do this drill anyway. I recommend you do this. Here are 7 questions. Try to pick the, ones that you think you have the best chance of getting, and, get as many right as you can. If you would like to then pause the video and do the rest, that's fine too. But I do think this is a good drill from time to time. Pick a number of questions, like open to a page in the official guide. Give yourself 2 minutes per question, figure out what that would be, and then cut it in half or whatever, and figure out, okay, go, how am I going to make these decisions? So with that in mind, I'm going to pull up the questions. I'll be behind the screen right now. I'm going to set a clock for 8 minutes, and then I'm going to go off screen. Ready, set, go. All right, gang, that is 8 minutes time. So we'll now we'll eventually kind of go through these and talk about how they relate to the topic we're discussing today. You can tally up how many you got right on your own. That's not really the point of the exercise or of the lesson today. But it is what we just did is a good drill in general. Set a clock for way less time and force yourself to make decisions about where you want to invest that time. Little just GMAT pro tip. Any question with Roman numerals is probably a good one to consider skipping. They tend to be real time sucks. And so if you start to get tangled up in those, it's probably a good one to save some time on. Okay. We'll go over them. We'll talk about them, but probably this one and this one, I think, are particularly difficult on this page. Not that the other ones aren't hard sometimes, but those are the real dragons, and I sometimes tell my students, you don't want to be a dragon slayer, you want to be an iguana kicker. Iguanas are small and they can't fight back. Dragons, boy, can they eat your lunch, and then you're in trouble for the rest of the test. I do not advocate for animal cruelty, by the way. That's just an expression. Find the iguanas, fight the iguanas. It's going to be way easier for you. So what do these questions have in common? You probably notice there's some similarities, right? We have a lot of inequalities. We have some exponents. So you might be thinking like, well, okay, we got like greater than 0. So kind of number properties, positive, negatives happening here. And I think that's pretty much right. But what we're really going to get in today is a specific kind of number property that the GMAT tends to test. And I've called this lesson the 4 sections of the number line. And what I mean by that, and every question that we just saw deals with this, the number line breaks into 4 basic sections that I've just chosen to label A, B, C, and D. Those sections are separated by the numbers -1, 0, and 1, 3 of the weirdest numbers in existence. It's helpful to remember those numbers for testing cases and various other things because they do weird things, right? You can add 0 to something and then you don't move. You can multiply 0 by anything and it becomes 0. You can multiply 1 by anything and it stays the same, right? These are important numbers to know, and they separate the number line in important ways. Okay, numbers in each section, A, B, C, and D, tend to behave a certain way. They tend to do similar things when you do math with numbers in those categories. So take a minute or 2 minutes here. I want you to think about the answers to these questions. Okay, what happens when you raise a number in each of these sections to higher and higher powers? What happens when you multiply a number by a number in these sections or divide? How might a product, sum, quotient, or difference end up in one of these sections between 2 numbers? And where do you see commonalities? Where do you see difference? So I just want you to think about numbers in these sections for 2 minutes here on your own and just brainstorm as many things as you can about the questions here. This free GMAT prep hour, as all free GMAT prep hours, unofficially sponsored by LaCroix. The only water I drink, apparently. Can't handle just regular water. It doesn't bubble and flavor my taste buds. It's got to be something fizzy. Okay, cool. So that's about 2 minutes. And if you're at home, I would pause and keep thinking, right? Figure out as much as you can on your own. That's the, work your mind out. That's the best thing you can do when you're studying. Force yourself to think as much as possible. For the sake of time, I'm going to talk through some of this here. Let's first talk about exponents, because exponents, you might have noticed just based on the number of exponents on that page are a fairly important part of this game. And exponents, when you raise numbers in these sections to higher and higher powers, different things happen depending on where the number is. The numbers we're most used to are D's, the numbers in section D. They behave like we think numbers should behave. We raise them to higher and higher powers, and those numbers just get bigger and bigger. They just keep jumping this way, right? Here's D squared, here's D cubed, D to the fourth is down, D to the fifth is down. It just gets bigger and bigger and bigger and bigger. Okay, we're used to those. Those are fairly normal. Therefore, of course, the GMAT doesn't use them as often on the questions like the ones we just saw. Or if they do, they're very sneaky about it. All the other sections do weird stuff, things that are much less intuitive to us and therefore take some figuring out. The ones in section C, if we raise them to higher and higher powers, okay, they actually don't get bigger and bigger. And if you ever need to test a number and check it out, that's fine. That will help you. But one thing I'm going to emphasize today is that with practice, you can understand and kind of reason through the patterns based on where a number is, rather than have to pick an actual number and deal with it. Because sometimes picking specific numbers can be frustrating, overwhelming, tedious, that kind of thing. So if you practice this enough, you can just have a sense of how the numbers behave. So if I take C and I square it, I actually get closer to 0, right? 1/2 squared is 1/4. I've gotten smaller. If I, take it to the third, 1/2 cubed is 1/8, smaller still. And these numbers just fold closer and closer and closer and closer to 0. They fold in towards that number. They never become 0, but they get close to it. Okay. Numbers over here, A in the A section, those are negative numbers less than -1. I guess you could just say numbers less than -1. If you raise them to higher and higher powers, they do something interesting as well. And this is the first time we're dealing with negatives. And you probably remember that a negative number squared will actually become positive. So that's one thing about the exponents, is that an even power turns that number positive. And then if you take it to an odd power, it will stay negative. And that's a good property to know. But there's also something else lurking in this lesson that I want you to think about. It's not just do they stay positive, negative, or flip positive or negative. It's what do they do in relation to 0. And A, when you raise it to the power of 2, it does go positive, and it also gets further away from 0 than A is. And if you cube it, it goes back negative, but it's further away from 0 still. You almost never have to deal with powers above 3, but that pattern continues. A to the fourth is positive again, and even further from 0, and then it's back negative, and it's kind of just blowing up away from 0. Okay, and then there's my personal favorite, the negative fractions, the numbers between -1 and 0. These do really fun things. Like negative numbers, they do flip back and forth, but instead of blowing away from 0, they tend to sneak towards 0. So B, if I take a B and square it, I'm going to be closer to 0 and positive. And then if I take a B and cube it, I'm going to be closer to 0 still, but negative again. And then if I take a B and take it to the fourth, I'm going to be closer and positive, and we spiral in and in and in towards 0, never actually reaching 0. And that's how these numbers behave based on exponents. And exponents are a very, very common feature of questions like this. If you see inequalities, exponents, and variables, you're almost certainly dealing with 4 sections of the number line question. Okay. But yes, there's also then the question of multiplication and division. So let's take a second and actually specify this. If X is some number, I'm not even going to tell you where it is on the number line. X is just some number on the number line. What do you know about A times that number X? What do you know about B times that number X, C times that number X, D times that number X? What do you know about X over A, X over B, X over C, X over D? Take a second, see if you can specify to yourself what you know about those numbers based on A, B, C, or D being multiplied or divided into X. Good, JD. What else do you know will happen? JD just brings up a good point. Ignore the numbers at the boundaries. Let's pretend X is not -1, 0, or 1. Especially 0. That's going to be the weird number with this problem here. While it is very useful to remember on the test that numbers might be -1, 0, or 1, for this exercise, pretend they aren't. Yeah, good, Kayleen. Okay, cool. So let's just talk about this. Again, if you're at home, keep brainstorming here. Let's start with the one we're most comfortable with, the most common with, probably D times X. Those positive numbers bigger than 1, you know, they don't necessarily have to be integers, but they're bigger than 1. They do the things we expect them to do. If we multiply X by D, it will move the number, especially if X is positive. That's the most common situation, or the most comfortable situation to deal with, right? If X is here, okay, X times D moves X over in this direction. It pushes away from 0 and bigger than X. Even if X is here, though, even if X is a fraction, a positive fraction, X times D does move in this direction. If you multiply by a number bigger than 1, any number, any positive number, is going to push away from 0. Okay. If X is here, we're going to push this way. We're going to get more negative, but we are still pushing away from 0. If we're here, we still get more negative if X is here, and we're pushing away from 0. And Kayleen has actually used the term, I think it's the first time we've used this term today, absolute value. That's also what's lurking here, is the change in absolute value. When you do operations with these numbers, absolute value is a measure of distance from 0. So if you multiply X times D, what's going to happen is you increase absolute value and you stay on the same side as X. If you do A times X, very similar thing. You're going to increase absolute value and you're going to move from 0, away from 0. But since it's negative, you know, you're going to flip signs from X. Since A is negative, not only do you move away from 0, you flip the sign. B and C do the opposite absolute value wise. Okay. B and C are going to decrease absolute value from X. And if it's B, you're going to flip signs from X. And C decreases absolute values. But stay on the same side as X of 0. To be clear, same side of 0 as X. Okay. So there's really two things to think about. Am I getting further away or closer to 0? And do I need to flip the sign or not? Those are the main things to think about here. Okay. For C, no matter what, the answer will get smaller. When you say smaller, do you mean, again, a lot of times we take smaller, we take it to mean less than, but it's very important to remember that smaller does not equal less than. The absolute value will get smaller. And so the absolute value will get less than, but it's actually possible to take a number and, you know, if I multiply this number, if this is X, let's use a different color. In fact, here, let's just erase all the stuff we had with the first scenario here. If I take a number here, X, and I multiply it by C, I don't know exactly where I'll be. I might not necessarily get past a -1, but I'm going to be closer to 0. And this is actually greater than x, right? xc is greater than x. The absolute value of xc is less than the absolute value of x. So you have to be very careful. It's very easy to get crossed up here on absolute value and actual value. It's one of the things to keep straight in this whole discussion. So yes, multiplying by b or c will definitely make the absolute value of the number. You'll shrink the absolute value. Okay. But be careful, it doesn't necessarily mean you make a smaller number if by smaller you mean less than. Just something to keep in mind here. I had a thought, what was it? I think well, yeah, I guess I could say this now. It's important to remember also that if I take x and I multiply it by itself, right, that equals x squared. Well, you can still think about what a number x does to numbers in that section, right? Whatever x does to numbers in that section, it does to itself when you, I don't want to finish that sentence. It does, whatever x does to other numbers in that section, if you do the same operation to itself, will do the same phenomenon, right? So a, if you multiply numbers in a to numbers in a, what you do is if you multiply a by any number, you're going to flip the sign and move away from 0, right? Any number in section A times a number flips the sign and moves away from 0. Well, if you take x, which is a number in A, and multiply it by x, a number in A, multiplying by x flips the sign and pushes away from 0. So x squared is going to move away from 0. So absolute value of x squared is going to be greater than the absolute value of x. And it's going to flip signs. Okay. I guess I should maybe use a, like a times a. If your x value is the same as your a value, the change is actually the same as if it were any other value in a. Okay. How about division? So that's multiplication. How about division here? What if I divide a number by a? Well, I'm going to flip the sign because I am, let's start with absolute value as we did last time. So the absolute value will get smaller, meaning we're going to get closer to 0. And we flip the sign. No matter what x is, okay? And again, if it's the same number, same rules. If you divide a number a by itself, a, in that section A, you'll end up at 1, right? But that flips the sign and gets smaller than, and the absolute value gets smaller. You move towards 0. X over b, the absolute value will get bigger and we'll flip signs. X over c, the absolute value will get bigger, and we don't flip signs. And in x over d, again, the one we're probably most comfortable with, the absolute value will get smaller, and we don't flip signs. Okay. If you really wanted to be like a gung-ho gunner for this, you could make flashcards for this number line and specify what every situation results in, right? You could split like a times a b. What does that happen? What does that do relative to a, and what does that do relative to b, right? A times b, first off, it's going to be positive because these are two negative numbers. We're going to be closer to 0 than a is because multiplying a number here times a number here pushes us closer to 0. We're going to be further from 0 than b is, because multiplying a number here by a number here pushes the number away from 0. So it depends which one you want to root in, but you can think of it both ways. You can think a times b, you can do a squared, of course. You can do c times a. Okay, we're going to flip signs, be closer to 0 than a is, but further away from 0 than c is. Of course, our favorite is d squared, because that's the most used to that. C times d, all that stuff. Okay. you really want to be a gunner about it, you can make flashcards and drill yourself on this till it really is intuitive. I wouldn't say you ever have to like have it memorized, but it's useful to be able to specify quick what happens to certain situations here. Okay, general things to remember. Are you flipping positive versus negative? Are you moving numbers closer to or further from 0? And in certain situations, this is less common, but it does show up. Are you going to be greater than or less than 1? And I don't know if I've ever even seen something about a relation to -1, but I guess it's theoretically possible that, or are you greater than or less than -1? Okay. These are the general things to consider based, what do numbers in this section, how do they behave? So a little quick drill here based on number line stuff. Go ahead and take, I'm going to give you 4 minutes for this. Specify what each of these tell you. Where, what do you know about the variables and where they fall on the number line, or where they could fall on the number line based on what this stuff tells you. Okay. What sections do these allow? JDS, do you visualize cases or you test cases? Again, if you get really good at this, you don't have to actually test actual numbers. It's still testing cases. That's the thing. We're not saying don't test cases here. It's just that you're testing cases of a section on the number line rather than testing actual numbers. And the more you've practiced that, the less you have to actually go to the specific numbers. You can just test the possible situations of the number line based on how those numbers behave on the number line. Okay. If you need to test numbers though today, go for it. But over time, you want maybe this to get a little more intuitive so you don't have to deal with numbers every time. And we'll see some of the questions we did today, or you might have done today in that intro. It's very hard to actually pick numbers in the time that you have. It's just very frustrating. It very much helps to have a good, strong understanding of this number line stuff. We'll see that down the road though. Take a minute or two here. All right, for the sake of time, again, I'm sorry for those of you that are watching this or that are here live. You don't have time to dig in as much as I would want to. If you're at home, hit pause, keep working, see how much you can figure out here. And also same thing for the people watching. I'd really love to talk through this and really meticulously go through this, but it's going to be a little bit fast just because it's a free GMAT prep hour and we don't have 2 hours to talk about this, although we certainly could. So if x squared is greater than 1, okay, what numbers on the number line does this happen for? Well, it's going to happen for numbers that are greater than 1 or less than -1. Certainly the numbers we're used to, those in D, but it also happens for numbers here, the numbers less than -1. Doesn't happen for any of the fractions because, again, if you square a fraction, it just gets closer to 0. Doesn't matter where the fraction is. So these numbers are the ones that when x squared is greater than 1, that's GMAT code for, hey, you're in one of these 2 sections of the number line. Okay, if x squared is less than x, this is a fun one because this actually only happens in one place. There's only one section of the number line that does this. It's not the negative numbers because negative numbers squared always become positive. So x squared is always bigger than x there. D, we're pretty used to x squared being bigger than x. It's going to be here, the positive fractions. If x squared is greater than x, you are on this band in the number line. You must be a positive fraction. It's the only place that works. X cubed is less than x. Well, that's going to happen in the section we just saw, right? In the positive fractions, any greater power shrinks closer to zero, okay? But this also happens here in the negative numbers less than -1. Remember that x, wherever x is here, right? We're going to go to x squared, which is further from 0, and then x cubed, which is even further from 0 still. So x cubed is going to be over there. Okay. Also, just a fun little fact, and I maybe should put this one here. Where is x cubed greater than x in the exact other sections? X cubed is greater than x. We're used to it here. That's pretty common. But also here, surprisingly, I think. It's a little bit unintuitive, but here, remember, if this is x, we square it, we're going to get closer to 0. And if we cube it, we're going to get closer to 0 still. So x cubed is greater than x, even though the absolute value is less than x. That's why I have to be very careful about the difference between absolute value and actual numbers here. Okay. The other thing I meant to mention, forgive me, is that, you know, with a lot of these, you might be tempted to do algebra. And sometimes you can. It's just that you have to be very careful about positives, negatives, and you don't know if a number is positive or negative. And really, I want you to try to not use algebra today to figure out, you know, like here, you can divide both of these by x squared and say that x is, or I guess not x squared, that's not a good example. I guess this one right here, for instance, where x squared is greater than x cubed. You can divide both of those by x squared and say 1 is less than x, or 1 is greater than x, okay? And that is accurate, right? These are the numbers where x squared is greater than, that's not true. See, now I'm talking myself into a corner here. 1 is greater than x. If I divide by x squared. Yeah, okay, here. So these numbers here, right? X squared is greater than x cubed. X is here, x squared is here, x cubed is here. But here's the thing, it feels like if we do the algebra that these numbers are also included. As they are, and they should be, excuse me, and they should be. Yeah, because a positive power and a negative number is always going to be bigger than that, right? So yes, this is a case where you could do algebra here, but there is one somewhere, and I'll find it eventually, where the algebra actually, if you really don't think about positive and negatives, it actually leaves a possibility out. And you want to be aware of that. So today, try to, as much as you can, kind of feel where the variable must be based on the behavior of numbers in that section. X cubed is less than x. We just did that one here. So how about this one? The absolute value of xy is less than the absolute value of y. Well, when does that happen? What's happened when we multiply by x in this case, we have a smaller absolute value, meaning we are getting closer to 0. Where do we get closer to 0? When we're on this band. If we're multiplying y by some fraction, doesn't matter what y is. If we multiply y by some fraction, we're going to be closer to 0. So x must be in that fraction band. This one's kind of fun. 0 is less than x over y is less than 1. So we know that this is where x over y is. When we divide x by y, we end up here. When does that happen? What does that tell us about x and y? Well, it tells us two things. First off, we know that this is positive. We know x over y is positive. So we know that they have the same sign. So we can consider the world where x and y are positive. Well, when do they end up less than 1? If x is less than y. I don't know where it is. It could be here. It could be here. There's infinite pairings of where x and y could be, but we know x is smaller and we know they're both positive, or the exact opposite. If they are both negative, choose a different color. If they're both negative, okay, and we end up at a positive fraction less than 1, then x is going to be to the right of y. It's going to be closer to 0. This tells us x is closer to 0 and they have the same sign. Okay. If the ratio ends up between 0 to 1. 1 over x is less than negative 1. So we know 1 over x ends up over here. Okay. Well, what does that tell us about x? X can't be positive because 1 over a positive number is going to be positive. It can't be a number in section A because 1 divided by one of those numbers is going to get us into the area B. And so what this tells us is that x itself is here. It's a negative fraction. Those are the numbers where if you divide 1 by those numbers, you're going to end up less than negative 1. Okay. Y is greater than x squared. This is just a fancy way of saying y is positive. Because x squared, no matter where it is going to be somewhere in the positive range, and y is going to be bigger than that. In fact, even exponents, you just want to keep an eye out for them. Develop a nose for them. They tell you positive or negative. We talked about x squared is greater than x cubed. That's going to happen for anything less than 1. Although be careful, it actually does not happen for 0 or negative 1. Those are weird numbers. It does happen for negative 1, excuse me. It does not happen for 0. So just be careful. Keep the weird numbers in mind as well. If the absolute value of x cubed is greater than the absolute value of x, that's a fancy way of saying that when you cube x, you get away from 0. So that's going to put us into the numbers outside of the ones. And if we have a product, 0 is less than xy. So we know xy falls somewhere in this range here. There are a lot of ways to do this. We do know they have the same sign. We do know they have the same sign. Do we know anything else about this situation? Yeah, good, JD. They can't both be in D. You can't multiply two numbers in D and end up greater than 1. One of them, I don't know which, but one of them has to be a fraction. They might both be, but they can't both be here. Very good. Same thing over here. They could both be negative because you can multiply two negatives and get a positive fraction as well. But one of them must be here and one of them could be anywhere. But we know one of them must be a fraction. So either x or y is in the band from the fractions, the numbers between the ones. And neither are 0. Again, I've been a little casual about these because I just am ignoring them tonight in many ways. But on the test, you have to remember zeros. It might be in play or might not be in play. You have to be aware of that kind of stuff. Okay. Whew. It's already 6:50. We still have the problems to go through. So this might end up being a GMAT hour and a half. If you have to leave, of course, feel free. Okay, but this is I do want to make sure we get through this lesson because I think it's a good one. I think it's one we want to have. So let's now go back to the problems that we first did and try to see how. I'm going to pull up a problem. I'm going to give you a minute to think about it and see how you can use this stuff about the number line on the question. If you want to try to redo the question, you can, but just take a second to brainstorm. How does the number line knowledge apply here? Oops, sorry. So notice the question itself is asking, is W in section D? Is W in section D of the number line? The statement that most applies to the stuff we talk about today is statement 2. It tells us W squared is greater than 1. Well, we've already seen what that means. That means maybe W is greater than 1, or D is in this section there. Okay. We haven't talked much about, nor will we talk much about today, addition and subtraction in relation to this game. If you actually search our free GMAT prep hours, by the way, these show up on YouTube. We do them every 3 weeks. And we have a whole library of stuff. If you search visualizing relationships on a number line, I think is what the video is called. It's similar to what we're talking about tonight. It's actually a little bit harder than what we're talking about tonight. I kind of wish I'd done this lesson first, but hey, if you're just seeing this for the first time, you get it first. But it kind of continues on this idea and brings in a little bit more addition and subtraction into this game of thinking about number line positionality. And so we don't talk much about addition and subtraction tonight, but we can do it here. If W plus 2 is greater than 0, well, that means, W must be somewhere in the realm of greater than -2, right? That puts us in basically this section of the number line on forever and ever and ever. Okay, so is W greater than 1? Well, if with just the statement alone, I don't know, it could be anywhere here in the negative purple band, or it could be over here in the positive purple band. Then we take everything together, and keep in mind, it doesn't tell us W is an integer. I think that would be important here. Yes, it would, because this would cancel out the possibility of -1. And maybe 0. Yeah, and 0. So notice, it's very important here to notice that we're not told W is an integer. Okay. And we have to have both of these be true. So we have to be both in the green and the purple. Well, we could be in that section we're so comfortable with, section D, but there is a slight overlap in the green and the purple here between -1 and -2. Though they're non-integers, but they are possible values of W. So it's very important. And this is just a big GMAT reminder, right? Notice when they say integers and notice when they don't. Some questions have to be integers, right? I can't have a half of a cow or half a rose or something, but I can have abstract fractions. And in abstract algebra questions like this, keep in mind that you can have non-integers. I think, JD, it is important. I think if you don't consider this possibility, the numbers between -2 and -1, you choose answer choice C, but the answer is actually E. We don't have enough to answer this question. The only numbers that fit both statements are the positive numbers bigger than 1, the numbers we like most, but there's also this band of non-integers between -2 and -1. These follow both statements' rules. The negative fractions don't follow statement 2's rule. -1 squared is not greater than 1. -1 squared is 1. So -1 is not allowed in statement 2. No worries. Okay. Take a minute and think about how you might use the number line knowledge on this problem. By the way, all the questions that we see today are from official practice tests. So again, these are things that show up on the test. So the question itself, we're told that on the number line, K is to the left of T. That means K is less than T, but we're not given much else than that. We know that we have this relationship. Where's 0, where's 1? No idea. but we do know k is to the left of t. They ask, is the product k times t to the right of t? We want to know if k times t is over here. Okay, well, when does that happen? And there are a few possibilities here, but this is a good chance to practice pre-phrasing and investigating. I think it's typically a useful thing to do. Okay. If t is positive, if t is somewhere over here, when is kt going to be to the right of t? What would make kt to the right of t if t is positive? They don't both have to be absolute values greater than 1. The question is not, is kt greater than 1? It would really just matter if k is in section D. If t is positive and k is greater than 1, that would end up with a yes answer. If t is positive and k is less than, k is here, that would result in a no answer. And of course, any positive number, if k is negative, k times t is going to be negative. So that's going to be to the left of t. Okay. So the only yes case here is if t is positive and k is in section D. If t is negative, when is kt to the right of t? Well, it turns out every case, because we know k is to the left of t. Wherever t is, k is going to be the left of t. And that's going to put us in a positive number, which will be to the right of a negative number. And again, ignoring 0, -1, and 1, but when we're told straight out less than 0, we might not need to think about it. So really, if it turns out if we know t is negative, the answer is going to be yes. And sure enough, here it is. T is negative. This is sufficient. So I know it's either A or D. This is a sneaky one. I almost just now thought it was insufficient, but I'm actually thinking about it. I think it is sufficient. Because if k is less than 1, if k is less than 1 and t is positive, you think about this. No, it should be insufficient. No, it should be sufficient. Yeah. Wait. Let me talk through it. I'll realize it as I talk. If k is less than 1, it's in this. It could be in this section. It could be a positive fraction. Well, and as we saw earlier, that would result in a no answer if t is positive. Okay. And if k is in the section, t would be positive because t is greater than k. So we could have a kt relationship where k is a positive fraction because it's less than 1. And the answer would be no. So if k is c, the answer to the question is no. K times t is not to the right of t. But if k is here, which is less than 1, and t is also negative, yeah. So if k is b and t is negative, the answer will be yes, k times t will be to the right of t. And statement 2 allows both possibilities. Yeah, it allows both possibilities. So the answer to this question is A. Any questions about that one? K is to the left of t, which means t is 1 or more. You're right. Okay, good point. So if k is here, if statement 1, if k is positive, t is here. And then, but still, kt is less than t. Kt is not to the right of t. So the answer is no to the question that is asked. If k is here, t would be here, and k times t will be to the left of t, so the answer is no. But if k is here and t is here, k times t will be greater than t because it will be positive, and so the answer will be yes. No, the answer is not always no, because you could have a k times t here. They're both an a. I think you were right. I think one of my examples was bad. I think the one where k was here and I kind of drew t here, that wouldn't be possible. If k is a negative fraction, t would be positive. And so the answer would be no again. But if k is in section A and t is somewhere negative, the product will be positive, which is greater than t, so the answer will be yes. Okay. I had a thought. That's a good point though, JD. One of my cases actually did break the rule and I shouldn't have used. I can't have k here and t here in this situation because k, oh yes, I can. I don't know why. We're gonna have to come back to this when the recording's off, JD, but I don't know why. There's nothing that says t is 1 away from k. I don't know why I thought that for a second, but there's nothing that says t is more than 1 away from k. Okay. Take a look here. How can we use number lines on this question? This one, it might be useful to do a little bit of algebra on. Here, x over y is greater than 1 tells us that there are two possibilities. Either they're both positive and x is bigger than y. And it doesn't matter. They could, here, if I have two fractions, x over y, since x is bigger, the ratio of x to y is bigger than 1, that means x is a bigger number. So if this is allowed, it could be two numbers here, y and x, y could be in C, x could be in D, but anytime x is bigger than y, this rule is going to be followed. However, it also allows the negative possibility where x would be less than y. Because a more negative number divided by a less negative number is going to flip signs, make it positive, and it's going to be bigger than 1 because x is further from 0. And so statement 2 allows both possibilities. It is eliminated. We're down to A, C, and E. Statement 1 tells us, if we do a little bit of algebra here, we do x minus y equals 1/2. Well, if you watch the visualizing relationships on number line, what this means is that x is 1/2 more than y. But are they both positive or negative? I don't know. They could both be positive, they could both be negative, or I could have a situation where I have y and x here. You know, they're straddling 0. And so statement 1 is not sufficient either. But if I take them both together now, well, I know, again, we're in one of these relationships, but if x is less than y, then x minus y is negative. Doesn't matter where x and y are on a number line. If x is smaller than y, x minus y is negative. Subtracting this negative number from x a negative number, is not big enough to cancel out x's negativeness, right? Just a -10 minus -8. That's going to put me in -2. That's still negative. So since I know that x is bigger than y from statement 1 by 1/2, and since I know that x over y is greater than 1, that means that we're in one of these two situations. I must be in this situation where they're both positive. X is 1/2 bigger than y. The answer here is C. Not testing numbers, not having to actually deal with that. You can. I'm not saying I'm not saying never do that. You've seen me do it. If you follow our videos, you've seen me do it dozens and dozens of times. But a lot of times I test cases with hypotheticals based on the number categories rather than having to deal with the gross specific numbers that could show up. I do both though. You're gonna have to do both. Okay, let's take a look at, we have 3 more, going strong. Now we're getting to the trickier ones. So I'll give you a little more time on this. We'll take a minute and a half or so. Just curious, go ahead and type an answer for this question when you have one. I haven't asked for answers tonight, but I'm just curious where the crowd is on this one. Okay, it's about 1:45 again for the sake of time. I'm gonna call it here. We want to know, is V positive? Is V on this side of the number line? Ahead of 0. They tell us this thing though, this MV is less than PV is less than 0. So I know the product of MV is less than the product of PV is less than 0. And so we can kind of think about number line behavior. And again, when you see something like this, it's often a good thing to do. You also might recall, if you've watched my rephrasing video on doing work before going to the question statements, which is in general a good idea. One good thing to ask is, what circumstance yield which answer, or which answers necessitate which circumstances? I think the second one is an easier question to answer here, right? If the answer is yes, if V is greater than 0, well, that would tell us, what about M and P? They must be negative, because if V is positive, but the product P times V is negative, these must be negative. Okay, so we know if V is positive, M and V are both negative. Do we know anything else about that situation? How would MV be less than PV if V is positive? Very good, JD, you see it there. M would be less than V. I'm sorry, P, excuse me, as you wrote. Credit where credit is due. right? This number is further away from 0 than this number. And if V is positive, it's because M itself must be further away from 0 than P. So that would be one situation where this rule is followed as it must be followed. And the answer would be yes, V is greater than 0. And also, by the way, this shows that none of the values are 0 because they're all less than 0. If one of them was 0, the product would be 0. So we know 0 is not in play for our variables. Well, what if V is negative? What do we know if V is negative? Those of you that are following along at home, pause and wrestle, strain, do as much thinking as you can. Yes, M and P must be positive because again, a negative times a negative would be positive, but we know these products are negative. So we know M and P would both be positive. What else do we know? And there you go, Krupa. In this case, M is greater than P. I'm sorry, yes, M would be greater than P because you still have to push this number further from 0. MV must go away from 0 more than PV does. That only happens when M is further away from 0 than P is. So we have two situations here that yield different answers. Either V is positive, M and V are both negative, and M is less than P. Or if V is less than 0, M and P are both positive, and M is greater than P. I might have said positive twice. Both negative if V is positive. M and V are both negative. Not M and V. M and P are both negative. And M is less than P. Or V is less than 0, M and B are both positive, and M is greater than P. In either case, M must be further from 0. Because we know they have the same sign. M and P always have the same sign. But M must be further from 0. And so this is the sneaky one here. M is less than P. That's this scenario. This is the scenario that follows this rule. And so if M is less than P, I know V is positive. And so I know it's either A or D. That's the harder statement. This one's a little bit easier. If M is less than 0 and MV is negative, V must be positive. If M is negative, V is positive. If M is positive, V is negative. M is negative, V must be positive. The answer here is D. But that first one is, I think, pretty tricky. A little bit of pre-thinking goes a long way on this question. But again, it's based on where they fall in the number line. We have to switch some signs and we have to push further from 0 with M times V. M times V must push further from 0 than P times V. So M must be further from 0. You either have PM if they're positive, or you have PM if they're negative. Yeah, so I mean, this is part of the issue with algebra, Asiya. If I have MV is less than PV is less than 0, you're asking, can't I just divide by V or divide by V and say M is less than P is less than 0? But that's assuming V is positive. When you divide by V, you don't know if you're dividing by a positive or negative number. That's the question. And if V is negative, you have to flip the sign. But I guess you could say, you could do this algebraically, right? And say if V is positive, I have this situation. If V is negative, you flip the sign and you have this situation. So you get to the same outcome. It's just using algebra, which is, I know I've said try not to use algebra tonight, but algebra is a tool. It's a tool that's useful. I just think you don't want to over rely on it. And we'll see some questions here in a hot second where you can't use algebra. So yes, you could consider same thing though. If V is positive, here's the situation. If V is negative, here's the situation. And statement 1 tells us that we are in this world. So the answer is D. Now we get the fun ones. That one's pretty fun though. Roman numerals, dreaded Roman numeral questions. Start with the easier one of the three. For the sake of time, I'm gonna go through this one a little bit faster. We know R falls somewhere in section C, and we know S falls in D between 1 and 2. We want to know which of one must be less than 1. But they're all positive, right? So this actually, we're done with this side of the number line for a second. We don't have to worry about it. Well, R over S, well, if you divide R by a number greater than 1, you move closer to 0. RS is going to be over here. Doesn't matter where R is, where S is, RS is going to be over here. Okay, so this must be true. This one's going to be less than 1 because R is less than 1. So that gets us down to A, D, and E. Okay. For these next two, does R times S have to be less than 1 and S minus R? We're going to have to go a little bit more advanced into our number line sections. And the questions we see for the rest of the day are going to deal with a more advanced understanding of the number line and the sections therein. You have the same 4 sections, but it's important to think about the extremes of the sections sometimes. It helps to think about the extremes. These numbers that are almost 0, those do different things than numbers that are almost 1 when you multiply, for instance. When you multiply by almost 1, you don't change the number all that much. When you multiply by almost 0, you almost get to 0, no matter how big the number is. You can make a number really close to 0 and get it almost to 0. Almost -1, I can't say it has shown up from memory, but it theoretically could, I guess. It also helps sometimes to think about BANs, bands, which stands for big numbers, and RFNs, which stands for really negative. I'll let you fill in the blanks. But those, like, 10 trillion, -10 trillion, just think about a ridiculous number that's so big you don't even have to worry about it. Think about how those behave. And if you ever really need one in the middle here, you can think about your 1/2 and 1/2, your -1/2 and 1/2. So the rest of the question today, we're going to deal with this more advanced version of the number line. We already know number 1 must be true here. So how about R times S? Does that have to be less than 1? Well, no. I know, again, S is somewhere between 1 and 2 here. If I take S, let's just put it where it is. Let's just put S right there. And I multiply by a number R, which is almost 1. I really don't move all that much. I basically stay at S. I can be so close to 1, it's basically 1, 0.999999999. So that could be greater than 1. And so this does not have to be less than 1. And so I can get rid of anything that has 2. So I can get rid of D. Okay. I could make it less than 1, right? If I multiply by a number that's almost 0, R times S is going to be almost 0. But if R is almost 1, R times S can be greater than 1, no problem. S minus R, similar idea, right? Well, if I put S here and R is almost 1, well, actually, that would be less than 1. Let's think about the case where it's not less than 1. Well, what if R is almost 0 for this last situation? S minus R is barely subtracting anything because I'm almost subtracting 0. So I don't move that much. And so I know that number 3 also doesn't have to be true. The answer to this question will be A. And you can pick actual numbers if you want, but I find it very convenient to just be like, okay, well, what if R is on this side of the extreme? What if R is on this side of the extreme? What happens? What happens when I multiply? What happens when I subtract? It can be helpful to think about these extremes in the categories. And on these last 2 questions, it becomes absolutely vital. So I'm actually going to put the the more nuanced version of the 4 sections here. And I want you to try this question again. Think about how you might use these categories to help you. Oh, yes, there's a typo here. D is option 2 and 3 only. I apologize. Pretty sure this should be this. Little typo. Okay, that's about 240. So go ahead and type in an answer. This is a very, very tricky question. Very challenging. The last 2 are very challenging. And I would say virtually impossible unless you think in this more advanced way. There's too many relationships to juggle to actually be picking numbers here. I think it's going to be an absolute headache. You might do it for practice and review to like really ground the discussion, okay? But I think this is really an example where you're going to want to have a more sophisticated understanding of the behavior of numbers in these sections and in the extremes and middle of these sections. So let's start with the easiest of the 4, number 1. And you might notice that only one answer doesn't have number 1. I can't remember a GMAT problem where a Roman numeral showed up in 4 of the answer choices and wasn't a thing, wasn't right. It's very rare for it to show up in 3 and not be right, okay? So just do keep that in mind. There's a pretty good chance that number 1 is going to work, and it does. And it's fairly straightforward, right? So we know, first off, we know x is greater than y squared is greater than z to 4th. One helpful thing to notice up front, what does this tell us about, let's just say x? What do we know about x from this relationship? We know x is positive. We know x is positive. It is not necessarily the largest, but it is positive because it can't be bigger than a number to an even power. So we know x is going to be on the right side of the number line. That's a guarantee. So statement 1, or the first Roman numeral here, x is greater than y. Let's just make x a BAN. It's just huge. Sure, it's bigger than y. It's bigger than y squared. That's, and that seems easy enough. And let's just actually make y a slightly less BAN where y squared is still less than x, and let's make z, z can be 1 or whatever, z can be somewhere less. It's not that crazy to think about numbers that have this relationship where x is bigger than y is bigger than z, and x is bigger than y squared and z to the fourth. You can make z a fraction if you want. There's several possibilities for this, but number one definitely works. So we're going to put it for sure as an answer choice. It's these last two that are more fun. 2, z is greater. So this actually, you might notice, puts the variables in the exact opposite order that they are here. And this is one of those, the GMAT's very interested in counterintuitive times, very interested in things that don't immediately make sense to us because it's wondering how well you figure out the situation. How can x be bigger than y squared be bigger than z to the fourth, but z be bigger than y be bigger than x, right? That's basically, that would look like this. We would have z to the fourth, y squared, and x, because that's what's given. But then they want us to say that that y is bigger than x, and that z is bigger than y. So it's wondering if we can come up with this relationship. Was there any way we can narrow this down quickly? Yeah, good, JD. Okay, if this works, if it works at all, I'm not sure it does yet, but if it works, it's only going to work here. Not negatives. No, not negatives, because a negative y can't be bigger than y squared. A negative z can't be bigger than z to the fourth, because these are positive numbers. If z is going to be bigger than z to the fourth and y is going to be bigger than y squared, we saw earlier, actually, there's only one place where that happens, and that's here in the positive fractions between 0 and 1. So at least we can narrow down number 2 and say, okay, well, if this does work, if it could be true, it could only be true in the positive fractions. So at least we're kind of narrowed down. From there, I think it's helpful to dig into the extremes, to consider where these variables might fall on this band such that this pattern emerges. And there might be more than one, but I found one. And that's if they're all basically 1. If I have x, y, and z in that order, very close to 1, where y is just barely bigger than x, basically the same as x, and z is barely bigger than y, basically the same as y. It's like 9/1000ths, right? That's not close to 1. It's like 996 1,000ths, 997 1,000ths, and 998 1,000ths. Now, I don't actually want to do these numbers. I'm not going to do any math with this. I'm just giving a hypothetical, right? Like, these are very, very, very close to each other. And they're also very, very close to 1. If I square that y, remember, if you square a fraction, it moves closer to 0. And so that's going to put y squared to the left of x. And if I raise z to the fourth, that's going to do that 4 times. And so, yeah, we're going to be able to follow this rule and have this relationship if they are right smushed up here close to 1. I don't think this will work anywhere in the blue band, JD. I don't think anywhere is going to work because x is greater than y squared is greater than z to the fourth. Well, I mean, we're about to see a situation that's different. So I know there's there's going to be a different situation that's possible here. Is that your point though? No, yes, it does step on your point because, like, for instance, I can do this as well. I mean, the answer here is E. But not every 3 fractions on this band are going to follow are going to follow this rule. That's the trick, right? We have to make sure this rule is followed. And not everything that follows that rule follows this rule as well. Right, like x can be 0.9, y could be 0.1, and z can be 0.00001, really small fraction, right? This is going to fit. This is going to fit everything in the blue, and it's going to follow this rule, but it's not statement 2. Z is not greater than y is not greater than x. X is greater than y is greater than z. As far as I know, the way to follow this rule best is to smush everything pretty close to 1. Or really, now that I think about it, I guess they don't have to be very close to 1, but they have to be very close to each other. So maybe that's what you mean, JD. As long as they're very close to each other, you can, yeah, that I buy. If I have x, y, and z very close to each other, anywhere in the fractions, then I can square y and put it here, and z to the 4th and put it here. And yes, that is true. You're right. So it's not that they have to be close to 1, it's that they have to be close to each other. Thank you. That's more accurate. They have to be positive fractions very close to each other. Cool. Good call out. I definitely had found the 3 that worked and just fixated on them without fully, and I should have thought more and be like, okay, but wait, are there other situations that could work like this? And there indeed are, but they have to be close to each other. I feel pretty confident about that. I haven't really even considered negatives. I might do that a little bit later. The fun one is this one also, because this is a little bit different. We now want to know if x can be bigger than z, can be bigger than y. I think it's easiest to make x a band. Just put x somewhere over here. Who cares? We're not going to worry about it because, yeah, then that follows all the rules. Everything's happy. The question is, again, how can z be bigger than y, but y squared be bigger than z to the 4th? Well, we actually have already dealt with that, though. If we make y and z positive fractions very close to each other, then y squared is going to be here, but z to the 4th is going to be here. And so it follows this rule, and the variables are in the order y, z, x. And so statement number 3 is also a possibility. I did think there was, I did think of a negative case here. If you had x's here and z, yeah, you could have like z could be 1/2 and y could be -1/2, for instance, right? Because that y squared is then going to go to 1/4 and z to the 4th is going to go smaller than that. So here you could bring in some negatives as well. There are a few different situations that would work for number 3, where you could bring in some negatives if you so chose. Okay, but all of these are possible. Again, I think this is a very hard question to do if you were actually picking numbers. And last but not least, the doozy of all doozies. Take a minute or so to think about how you might use our lesson on this. And I promise we're almost done. Turn into a GMAT, free GMAT hour and 40. Oops, spoiler, that's okay. Pretend you didn't see that. This is nice that we have gotten rid of this because x is positive, so that's nice. Could be questions are always a bummer because it's could be, it's not must be, right? If it's must be and you find any numbers that don't work, then that answer doesn't work. But could be, you have to find a case that could theoretically fit that relationship. And it might be a rare case, might be a hard case, and to prove something that doesn't work is fairly tough because you know how many things you're going to test, right? How many numbers you're going to test to find the one that how many you're going to test that don't work before you decide I just don't think this works, right? That's always a tricky thing. So it's hard to prove that you can never actually find the case that works in this situation. But notice all of these questions give us a little hint. We're told that x squared is always smaller than 1 to the x, or I'm sorry, 1 over x. So what does that tell us about x? When is x squared less than 1 over x? We know x is going to be a fraction. We know x has to be in this realm. So we're actually only dealing with fractions. There's no other possibilities here. I guess 2x it's worth considering maybe that 2x might pull us ahead. But for x itself, we're only in this world. It is also worth remembering that 2 itself fits a category. 2 is in section D. It behaves like all numbers in section D do. When you multiply a number, a positive number by a number in section D, you're going to move bigger. You're going to move away from 0. 2 moves numbers away from 0 in multiplication. It's going to be important here in a second. Okay, so could we have a situation where x is a fraction and x squared is less than 2x is less than 1 over x? Krupa is saying x could be very close to 0. I think that works. I think, in fact, it's true it could, or it could, I think it could even be close to 1. I think that will still work. Maybe not with 2x. I think close to 0 is probably easiest, right? If x is a very small fraction, yeah, x squared will be very small. 2 times that number, because 2 is in section D, is going to be bigger, right? And in fact, it's also worth remembering that x squared is going to move numbers closer to 0 from x, because x is a fraction. So x squared is small, 2x is bigger than x, right? X is somewhere here. And then 1 over that little number actually becomes pretty big. The closer you are to 0, when you divide 1 by that number close to 0, you actually end up in band territory. So number 1 could totally be the order of these 3 things. So I know it's not none, and I know it's not 3. Again, notice that number 1 shows up in all of them. So it's probably the case. Now, it also was somewhat easier than these are going to be. And so I'd probably be skeptical of answer choice B in this case. If one of them is easy and the other 2 are hard, you probably want to err towards D or E. Don't cling to the one that's easy. That's just a good GMAT tip in general. Go out on a limb, even if you're not certain. It's better to guess D or E at this case. Okay, so how about this, where we have x squared is less than 1 over x is less than 2x? I found the case best to use here to be numbers very close to 1, to be a fraction very close to 1. I don't know if it's the only one that works, but if x is almost 1, x squared is going to be less than 1. Right? 1 over x, well, 1 divided by a number really close to 1, but a little bit less than 1, is going to be a number very close to 1, but a little bit greater than 1. Right? 1 divided by 99 over 100 is 100 over 99. It's very close to 1. It's just on the other side. And 2 times a number very close to 1 is very close to 2. So I can have my x here, my x squared here, my xb here, my 1 over x here, and 2x here. And so number 2 also works. And so I know it's not B. I already kind of suspected it wasn't B. The question is, can we get number 3 to work? Well, X is somewhere here. We know X squared moves this way. And we know 2X moves this way because 2 is in section D. And so there's no world where a 2X can be greater than X squared if X is a positive fraction, and X must be a positive fraction because that's the only situation that follows this rule. So the answer is D. This one does not follow. Okay. Can you divide by X to get 2? Well, if you divide by X, you're going to get 2 is less than X is less than 1 over X squared. Now, the X doesn't cancel on the last one, JD, but it's still, you divide 1 over X by X, you don't get 1. You get 1 over X squared. Which might show you that this is impossible, now that I think about it. Because X is a positive fraction. So 2 can't be less than X because X is a positive fraction. So yes, you could use algebra as well. You could divide by X because X is positive and realize, well, 2 can't be less than X because I know it must be a positive fraction. I know it's a positive fraction because X squared is less than 1 over X. That does not happen for numbers in D, in section D. That only happens for numbers in section C. So you still need to use a number line knowledge, I think, to make this clear. But yeah, you could theoretically divide by X. Okay. So main takeaways here. There are the 2 versions of the number line, the more simple version and the more nuanced version that gets into some extremes within the sections. But most commonly, you're going to deal with the 4 sections: less than -1, a negative fraction, a positive fraction, or bigger than 1. And do remember the weird boundaries. What happens at 1, what happens at 0, what happens at -1. When you see variables, inequalities, exponents, absolute value, or distance from 0, relationships with 1 or 0, or relationships between 2 variables, you're likely in this territory. Roman numeral questions also tend to be in this territory. Okay, it helps to have some familiarity with how numbers behave. Okay, you can make flashcards, you can practice with it, you can use real numbers for a while until it becomes more intuitive. But it helps to have a sense of how numbers behave when they're in these different sections and when they're in these extremes within the sections. Right. If you multiply, if you multiply a number in D by a number in C, you're going to move left from D. You're going to get closer to 0, but if you're really close to 0, you're going to get a lot closer to 0. And if you're not that close to 0, you're going to stay pretty close to D. So you can go, into that second level analysis of the relationships. Okay. Be aware how products and quotients end up in these sections. Sometimes sums or differences, but usually it's products, quotients, or exponents. Primary issues closer to further from 0, sometimes by how much closer or further from 0, or 1. Does the sign flip? Are we less than or equal to 1? Less than or greater than 1? And again, look at those extremes for more complicated situations. That's it. Free GMAT hour 50. Free GMAT prep 2 hours. If you're looking for upcoming courses, visit that link, manhattanprep.com/GMAT/classes. You can attend the foundations course for free. You can try the first course of our full course for free. I recommend everyone do those no matter where you are in your studies. Full honest disclosure, I meant to say this at the beginning. So for those of you that have held on this long, I thought about this topic this morning. I really I was trying to think about what I could teach, and I'm kind of, truth be told, I'm running out of stuff. I really do feel like we have covered so much of the big stuff in these free GMAT prep hours that, you could watch them and make a full GMAT curriculum out of it. And if you actually look on GMAT Club, I've kind of listed a introduction crash course, more than a crash course really though, that covers all this stuff and gives, you know, what I think are the main things you need to get a great score on this test. I'm kind of running into like little things, you know, we probably need to do some geometry, like rectangle stuff. We haven't had much on rectangles on the free GMAT prep hour. And like, I could get into digits and decimals, but like, these are smaller subtopics. The big stuff, the strategies, the habits, the study habits, the major mechanics, like it's all out there now. I feel kind of like I'm running out of ideas. So why am I saying all this? I'm saying, email me what you want to see. Email me your questions or hopes for a free GMAT prep hour. My email is rarnold@manhattanprep.com. Do topic GMAT prep hour ideas or prep hour idea. Okay. For those of you that are watching the recording, you know, if you can't make these live, but you want a recording of a lesson, let me know. Again, I've covered so much of the big stuff. If there's something we haven't covered yet that you want to see, it's probably, again, a smaller topic of some sort, but shoot it my way. We'll do a free prep hour on it. But the big stuff, friends, it's out there. You can really learn some big things from our prep hours that have already been made. Okay. So I'm going to go ahead and stop the recording now. I thank you all for sticking with me. But I will hope to see you all soon. Again, we do this every few weeks or so. Shoot me some topics. Let me know how I can help. And best of luck in your studies till then.